Hi everyone, welcome to this session. We shall be discussing about a transformer calculation with various connections. Remember previously we have dealt with various transformer connections where we happen to have mentioned about star-star connection of a transformer, delta-delta of a transformer. We have also looked at star-delta connection of a transformer. We have also looked at delta star and star delta. And remember, what happens is if you are given star delta, it means the primary is connected in star, then the secondary is connected in delta. If you are given a delta star, the first one represents the primary and the second one represents the secondary. So we're going to look at an example and we draw the diagrams for that particular question. So the question reads, a three-phase transformer has 500 primary turns and 50 secondary turns. If the supply voltage is 2.4 kV, find the secondary line voltage on no load when the windings are connected in. The first case there is a star delta and the second case is a delta star. If you look at the solution, I have drawn a star delta connected circuit whereby the primary is star connected and the secondary is delta connected. For you to be in a position to solve this question, you must remember a few concepts about a three-phase power, a three-phase system, about three-phase supply system, whereby we know the relationship between a delta connection and a star connection parameters, especially voltage and current. We know in a star connected system, the phase voltage is equal to the line voltage divided by root 3. Whereas in a delta connected, the line voltage is the same as the phase voltage. For a situation of current, we know in a star connected system, current in the line is the same as current in the phase, meaning the phase current is equal to the line current. But for a delta connected system, the phase current is equal to the line current divided by root 3. These are some of the concepts basically we must be having to be in a position to solve this particular example, So you look at the first example there, the first part of that question, which says star delta. So basically what we shall do is, we have been given the line voltage. Which is equal to 2.4 kV. Remember this one can be written as, this is kV. Remember this one is the same as 2400 volts. 2400 volts as the primary. So if you want to get the phase voltage in the primary, we are going to denote it as a VP, meaning the phase, or we can call it a PH to represent the phase voltage. It will be the same as the line voltage divided by root 3. This one will be equal to 2400 divided by root 3, which will be equal to, remember we are saying if you want to get the phase voltage in a star connected system, you will take the line voltage of that system, you divide by root 3. So we are having 2400 divided by root 3, you will get 1385.64. 1385.64 0.64 volts as the primary voltage. And remember, whenever you want to transform, remember we know we have a transformer ratio. The transformer ratio is meant to assist us to transform voltage from one side, either primary to the secondary or from secondary to the primary. And we can only transform phase parameters. We cannot transform line parameters. So whenever you want to transform, ideally you need to get the phase parameters. That is why we are forced to get the phase voltage. Remember, the question asks us to get the secondary line voltage. We have gotten the primary phase voltage. We need to know the transformation ratio K. Transformation ratio K. Transformation ratio K is equal to we are using the secondary number of turns all over. This can be given as N2 over N1, which is equal to, remember we have been given a three-phase transformer has 500 primary and 50 secondary, meaning these are N2, these are N1, these are N2. So we have 50 all over 500. That is a ratio of 1 to 10. That is a ratio of 1 to 10. So our K, basically our K is equal to 1 over 10. Our K is 1 over 10. Remember, we also know the transformer equation. Transformation equation K is equal to N2 all over N1, which is equals to V2 all over V1. V2 over V1, this V2 and this V1, this is the secondary phase voltage, this is the primary phase voltage. Remember, we have said you can only transform phase parameters. Because we are being asked to get the secondary voltage, then it implies that the secondary voltage is given by, you multiply this by K. You can multiply this by K, then that means you will be having N2 all over N1 multiplied by V1. So therefore, V2 will be equal to 50 all over 500 multiplied by V1, which is 2400. If you divide, this one should give you, if you divide, that one should give you 240. Should give you 240 volts. 240 volts as your 240 volts as your secondary voltage. 240 as your secondary voltage. There is somewhere we have messed this one. This one, remember, is not 2400. We have said you are only transforming the phase voltage. So V1 is actually 1385.64. So if you solve this one, you will be able to get 138.564. 138.564 as your value. So the value there is this is 138.564. 138.564 as the secondary voltage. We now move on to part B. Part B requires us to draw a delta star connection. You can see the primary is delta, the secondary is star. Remember, this question you can be asked to draw the circuit itself, besides taking the calculation. So what we shall do is, So what we shall do is we will get the primary voltage. We remember we have been told the supply. The line voltage is 2400 volts, and remember the phase voltage is equal to 2400 as well. Remember we have said in delta the line voltage is equal to the phase voltage. That is why the line voltage is equal to the phase voltage. The transformation ratio K, we know K is equal to 550 all over 500. That is N2 over N1, which is the same as 1 over 10. 1 over 10. Remember our intention is to get the secondary voltage. We know K is equal to N2 over N1, which is equal to V2 over V1, right? This one now will be the same as V2 will be equal to N1 multiplied by V1 I think that is clear because we have done it in the previous example. So that tells you that the secondary voltage V2 will be equal to N2 over N1, that is 550 over 500 multiplied by the phase voltage, which is 2400. If you solve this, your secondary voltage, if you solve that, your secondary voltage will be equal to 240 volts. So that is the secondary voltage. That is the secondary voltage. Therefore, the secondary voltage becomes 240. Remember now, the question is very simple. We are being asked to get the secondary line voltage. This is the secondary phase voltage. The secondary phase voltage. So if you want to get the secondary line voltage, this is a V2. The secondary line voltage VL will be equal to 3 V2. So you need to take, if you want to get the secondary line voltage, I'm saying, you will have to take that value, you multiply by √3. Remember we have said in star, for star, the line voltage is equal to √3 V phase. Remember this is the same as √3 V2. So our V2, in that case, we have gotten our V2 to be 240. So the line voltage there will be equal to √3 times 240. If you take 240 multiplied by √3, you will get 415.69 volts. This is now the secondary line voltage. The secondary line voltage of that particular circuit. So that is how basically you handle these questions. You must be having the basics on the three-phase system so that you can be able to maneuver.